So yeah, it looks like the circuit is dead due to overheating on the power MOSFET. Yeah, I'm gonna have to check if it's damaged at all. Oh wow, it is. It's not damaged, but the high temperature is desoldered the chip, so it dislocated, so it's no longer working, that device. Can we use two BJT transistors and a battery pad to charge out your phone? That's what we're trying to find out in this video. The other day I came across this rather simple 5V BJT voltage regulator on the channel called Tech Insert, and it uses only two BJT transistors, two resistors, and one potentiometer. It claims to be able to output a voltage between 0.7 volts and 5.2 volts, and the supply voltage maximum rating is less than 28 volts. And since it's called 5V BJT regulator, I was wondering if we can actually use this circuit to charge our phones. So in the channel Tech Insert, it also does not explain how the circuit works, and it only shows you it actually does work, but it doesn't really show you why it works. So in this video, we're trying to figure out why it works. All right, the first way we analyze this circuit is by zeroing out RP. RP is basically the potentiometer here. Okay, once you zero out RP will become a wire, and it is so that the VL output voltage is going to be directly connected to the base of Q2 right now, right here. So in this configuration, there's a 0.7 volts of voltage drop across the BE junction of Q2, and that means there's a 0.7 volt of voltage drop across the BE junction as well. Okay, that's because these two junctions are basically diode. Okay, so the output is going to be VL. It's going to be 0.7 volts. Okay, so after you zero it out, another way of looking at it is you max out RP. If you max out RP becomes a 10K resistor. Okay, so once it's 10K, that in this condition, the Q2 is still 0.7 volts. Okay, it's maintaining at 0.7 volts. Now, since you have a 10K resistor here, there's current coming down here through R2, and there's current going through the base to the emitter. These two currents, okay, sum up here. Okay. So this is going to be a sum of these two small currents going through RP, and that's going to raise the voltage of output, okay, by a certain amount. It's no longer directly connected to 0.7 volts. It's going to be this current here, IRP, times the 10K value here. Okay, so in this case, you know, we actually have a pretty simple way, simplified way to actually calculate the voltage at VL. If you assume this base current is going to be small, it is going to be small because that small current here will induce a large collector current, okay, on this side. Okay, once you induce a large collector current, you drop the voltage at the base of Q1. Okay, obviously there's a 0.7 volts here as well. It's gonna be a diode junction here. Okay, that will reduce this voltage. That will reduce the current going through the IRP. It's gonna be smaller. Once IRP gets smaller, this base current will be smaller as well because it's a sub part of this large current IRP. So this current is going to be small because if it's big, the drop across here will be big, and that will reduce the current coming down. So it becomes a negative feedback basically. Okay. So we assume like the base is zero, and base current here going through will be zero because it's small compared to the current going through R2. So after that simplification, obviously it's going to be larger than zero, but we just simplify it so that it's easier to calculate. Okay, if we assume there's 0.7 volts and then there's just this one current coming through, the current going through R2, we can calculate that IR2, the current going through R2 is going to be it's around 0.47 milliamp. Okay. All right. So if it's 0.74 milliamp and the current coming down the RP and R2, you can calculate the voltage VL very simply by using Ohm's law. That is VL is equal to RP plus R2, okay, then times the current here, IRP. Okay, that will be 0.47 and times 11.5K. That will come out to be 5.4 volts. Hey, that's pretty close to that 5.2 volts claimed by the author of that video at Ted. So that's the sort of easy way to look at why the output range is between 0.7 volts and 5.4 volts. Okay, now we have the circuit built, so we'll take a look at how it performs. Now, first of all, we have this 10K resistor right here as the potentiometer. So it shows here the output voltage is 5.2 volts. That's very close to our calculation. We said that we estimated it to be actually, let's see. Yeah, we estimated it to be around 5.4 volts, but actually it goes out to actually the actual measurement is 5.2, so it's pretty close. Okay, now we can short this resistor, short it out, basically setting the potentiometer to 0 by using a single wire here. Okay, let's short it out. Yep. Once you short it out, as you can see, it becomes 0.77 volts. That's the diode drop of the Q2 transistor, which is now directly connected to the output. We can see here that if we zero out in the scenario where zero out the RP, that RP becomes a wire. Now the output connects directly to the base of Q2, making that output 0.7 volts. Let's look at the thermal here. As you can see, now the most the hottest element in that circuit is the, sorry, let me zoom in here, is the transistor R1 here, because since the output is so low right now, most of the stress, most of the voltage can be drawn across. The output is 0.7 volt here, so the most of the supply voltage is going to be across the R1, making it pretty hot. Take a look at the thermal here. Yeah, it's a stabilizing around 52 degrees. Yeah, so we can just disconnect this. Now the voltage goes out to 5.2 as the output. So yes, the spec says that this circuit can go out to 28 volts in terms of supply voltage, and we're trying to figure out why it is so. Okay, why 28 volts? I think it's because let's say we put the output at 0.7 volts, which basically zero out the potentiometer here, and that will put most of the stress across Q1 and R1. Okay, if you don't have any loads connected, the current will just flow through the collector. There's some small base current here, but it's not a lot, so it's not gonna generate a lot of heat here. It's not gonna generate any heat at all because there's no, well, actually some sort of a little bit of heat, not a lot, because the current is small. Okay, and there's a 0.7 volt here, so it's 0.7 over here at the output. And since the output is only 0.7 volts, most of the voltage is going to be across R1 and Q1, the supply voltage. And in this case, Q1 is not going to take a lot of current because it doesn't have any load, but a lot of current is going to go through that R1 resistor here, causing this unit to heat up. It's not going to heat up the Q2 because the voltage is only 2 times the diode drop, which is 1.4 volts. So there's not a lot across Q2. So I think the thermal limitation on R1 is going to limit the VS to 28 volts around that area. So that's my guess right here. All right, the next thing we're going to do is take a good look at the supply voltage limit. See how far high it can go. And the setup is so that the low is 5.1K. We put a resistor here as a low. And that potentiometer is going to be a wire. So the output is going to be 0.677 volts. Basically a diode drop on the base of Q2. So let's take a look at the thermal image of the circuit. As you can see right here, it goes up to 67 degrees at the voltage of supply voltage of 15 volts. Okay, so we're gonna increase that higher voltage thermal point. It's actually the resistor R1 here. That's the resistor going into the base of Q1 and the collector of Q2. Basically, most of the voltage is going to be drawn across this resistor because the output voltage is so low that basically the voltage going across the R1 is going to be twice that. The supply voltage subtracted by twice of 0.677. So at this point, it's about 1 volt, a little bit 1 volt less than the supply voltage. So at this point, it's going to be 14 volts, and close to 14 volts across that resistor here. Let's increase the supply voltage even more. We're getting at 20 volts right now. 20 volts. Okay, that already goes out to 80 degrees. Let's go to 27. It shoots up to 100 degrees, over 100. Let's go even higher at 32.6, which is the highest my bench supply can go. As you can see, it's already at 160 degrees. That resistor is still doing good, I suppose. It's not breaking down, but if you go any further, something close to 40 degrees, I think it's gonna break down at some point. The current right now is at 20 milliamp. So at this point, it's consuming about 600 milliwatts of power through that resistor. Quite a bit of power actually for a resistor. I think it's supposed only to take something like, I don't know, 250, a quarter watt. So it's already over that limit, 200 degrees. That's the output voltage is stable at 0.7 volts. So you can see the limiting factor of the circuit is that resistor. Okay. Obviously, as you increase more and more of that supply voltage, that resistor gonna consume more and more power. A lot of power is gonna be wasted on that resistor. So, and you wouldn't want to go very high in terms of output supply voltage, as you can see. So last thing we're gonna look at is whether or not this circuit can be used to charge our phones. Unfortunately, it cannot, because the charging currents go through Q1's collector emitter path here, and the 2N 9304, and most of the BJTs cannot sink that much current, because you something like about 1N at least for charging phones, but sometimes it can go out to 2.5 N, and that's 12 watts of power going through Q1. It just cannot sink so much current. You can only sink 200 milliamp of current. So unfortunately, it cannot. Right now, we can look at the output voltage at 5.16. Let's plug it in here. Light turns on, it's charging at 200 milliamp, 210. So look at the thermal here. Okay, it goes out to 100 something degrees. So the maximum it can sink it's 100, 200 milliamp, and the voltage drops significantly. So the BJT here, it's not very good current sinking device. It can at most sink something like 200 milliamp, and it's heating up pretty badly. 100, 160, 170. Let's take a look at it. 200 degrees. If we continue like this, it's gonna burn out, basically, I think. 200 degrees. Okay. So as a charger, it's not very good because the voltage drops significantly, because it just cannot source enough current from the power supply. But we can actually do better by using a BJT. Power MOSFET. Power MOSFET can actually sink a lot of current. So we're gonna do a lab here by replacing BJT Q1 with a power MOSFET. We'll see if you can actually charge our phones. So we made this adapter board for a power MOSFET. I've said that you can actually use power MOSFET to actually sink a lot more current. So in this case, we just did that. We did a modification to the device, to the circuit, and now we should be able to charge out devices such as this. Let's do that right now, and let's connect it. Let's put it here a little bit on. So let's connect the device. The light switch is on, meaning it's charging at 500, 600, around 600 milliamps. Let's look at the thermal. As you can see, the thermal is shooting up on that power MOSFET. It's now around 90 degrees, still rising. Remember, we don't have any heatsink solution for that MOSFET, so it's heating up nicely. It goes up to 180 degrees now. Wow, 190. So yeah, most power is gonna be lost in that device here, in that power MOSFET, but we're still charging. And that let's look at this this voltage is holding stable 5 volts. However, that temperature basically stabilizes at 155, 160 is still kind of rising. Yeah. So, well, actually, look at the current here. It's 720. Actually, yes, it stops right now. So let's look at the 150. So yeah, it looks like the circuit is dead due to overheating on the power MOSFET. Yeah, I'm gonna have to check if it's damaged at all. Oh wow, it is. It's not damaged, but the high temperature desoldered the chip, so it dislocated, so it's no longer working, that device.